Okay, good afternoon, ladies and gentlemen. My name is Sugimura, and I'm chairing the session. Welcome to the 53rd WPI I²CNER seminar series. And today we would like to welcome Professor Jean-Michel Martin from Ecole Centrale de Lyon, France. I think this is the first time we invite tribology professors for speaker in WPI I²CNER. And so you are the first tribologist in seminar series. And let me introduce you briefly. Professor Martin is a very distinguished tribologist. We know him very well, and he's one of the top leading tribology researcher in the world. And he published many papers, and he obtained many awards. He obtained PhD degree in 1978 from Claude Bernard University. I'm sorry, this pronunciation is bad. In Lyon, France. And he became a professor in Ecole Centrale de Lyon in 1988. And since then, for maybe more than 30 years, he devoted himself to the research in tribology. And his research interest extends in many fundamental and application areas in tribology, including boundary lubrications, thin films, coating films, extreme pressure additives. It's a more chemical rather than mechanical side of tribology. And today we have his lecture from gas phase lubrication, and I asked him to talk about something related to hydrogen, because we here in Kyushu University, we work on tribology in hydrogen or hydrogen effects in tribology. So now let's welcome Professor Martin.
Thank you very much, Professor Sugimura, for your kind introduction, and also for inviting me to Kyushu University and to visit the laboratory and to give this talk. So, now it's working. Okay, so today I would like to talk about what we call tribochemistry, and a special field of tribochemistry, which is gas phase lubrication. It's a lubrication by gas, but not only for application, but using the gas to simulate additives in liquid lubricants. So this is my Boucher, who is assistant professor, and this is an engineer who conceived the machine. So our laboratory is in Lyon, not exactly Lyon, but Ecole is a small village near Lyon. So first of all, I would like to talk about thermochemical reaction. So this tribochemical reaction are a reaction induced by the friction. So this is a schematic picture by Professor Nakayama. And as you can see here, you have two pieces in sliding. This one is sliding in this direction. And here you have a contact area. And in this contact area, the energy is dissipated. And this energy is dissipated in heat first, 90% maybe dissipated in heat. So you have temperature increase in this area. The second point is that here, if the two materials are not insulating, you can have charging of the two materials and a plasma. You can have a plasma discharge in this area. So this has been shown by Professor Nakayama in Japan. It's very, very well documented. And this triboplasma can modify the surface chemistry behind the contact, but also inside the contact, and maybe sometimes before the contact. That's the triboplasma. After that, a little bit long distance from the contact area, we have the surface has been tribostressed, and electron can be emitted from the surface during a certain time. We call exoelectron emission. These electrons can react with the molecules of the lubricant and change the surface chemistry again. And lastly, the surface here is tribostressed, but if it is a metallurgical surface, you can have defects, plasticity, dangling bonds in case of plastic deformation. And this also will modify the reaction of the lubricant, which is here, to come to the surface. So typically, this is a quite complex situation. And our strategy was to use a vacuum chamber here to put the sample in a high vacuum chamber. And in this vacuum chamber, we can, if we want, remove the oxide layer, for example, on steel, and have a friction of iron on iron. After that, we can make a friction under UHV condition. After that, we can introduce the gas and make the friction in presence of the gas. And finally, we pump up the gas, and this can be transferred to analytical chamber for surface analysis. So we can identify the chemical reaction occurring by XPS or Auger. If this time is sufficiently high, for example, after 30 minutes, the temperature, triboplasma, exoelectrons cannot be produced. So we have only this surface activity here. We can manage the reaction of the gas with the surface. So this is a strategy of that. And with this strategy, we can study several things. First of all, the reactivity of the nascent surface with the gas by using this sequence here directly, 1, 2, 3, 4, 5, 5. We can also study gas phase lubrication, so the lubrication in presence of the gas. Typically, we can change the temperature of the sample, minus 100 to 500 degrees, and the gas can be controlled between 1 hectopascal and 2,000 hectopascal, so typically 2 atmospheres. And the condition here, this is a pin and the disk, and this is an hemispherical pin, and the pressure is 200 Newton and so on. This means that we are typically in a hard working condition. So the tribometer is something in this part here, and after the test, we have to transfer to the analytical chamber here. Sorry. So the advantage of this method is to simplify the tribological system, because in presence of gas, you have no hydrodynamic lubrication. But you can introduce several gas, so to study the mixture of molecules. You can control the contact surface, remove the oxide, clean, remove the contamination and even the oxide. And you can, of course, analyze the surface. There is some limitation, of course, because you can only introduce light molecular weight molecules to have a gas, a pressure. And this is maybe another drawbacks. Yes, this is compared to the liquid phase. It's not very different if you use a high pressure of gas. I will show you later. So this is typically our mesh. This is a tribometer pin here on the flat. This is to measure the friction force here. And the machine, the tribometer is here. And after the test, we can transfer here. We can transfer both the pin and the flat for analysis. This is looks like a machine. You know, you have this kind of machine in your university, quite complex system. Okay, so I would like to show you some example. that we did in the maybe 5 past years. First, I would like to show about sulfide, phosphite, borates, titanium alloys, and also hydrogen to put here with carbon. So to modelize a molecule used in practice, we have to shorten the carbon chain, because otherwise we cannot introduce as a gas. I will show you. Okay, it's that way. So, for example, this is a problem of cutting of metals. In the cutting of metals, you have nascent surfaces formed, and the surface react immediately with the molecules which are in the lubricant. So we try to simulate this very complex situation. So we use 2 molecules here. This one, this is hexane-thiol, which is, and this one, it's more complex structure with a sulfur, but this is an industrial additive used for cutting. So we would like to study the interaction of these molecules with the new surface forms after the cutting operation. So we used the strategy like I tell you, first in vacuum. Here we remove the oxide because the nascent surface has no time to oxidize in the cutting operation. And after we make the friction in vacuum, expose to the gas, make the friction in the gas, and pump to analysis. This maybe takes about 3 or 4 hours to make this whole operation. Here, you have the surface after the test. So in this blue area is a ion-etched surface. The oxide has been removed. So if you look at the analysis here, this is Auger spectrum. You see only iron and a little bit of carbon contamination. No oxygen here is very small. No, but practically no reaction with the sulfide. If you look at this red spectrum, we come from here. So this here, the friction has been made in vacuum and after exposed to the gas. You have the presence of the sulfur peak. So this indicates that the molecules react with the tribo-stressed surface 30 minutes after. And of course, if you analyze inside the well scar, you have a lot of sulfur here. And even here, you can see there is a peak, is the 2 contribution to the peak, and this is a Auger standard spectrum. This peak here is a carbide. So the hexane-thiol molecule here has been cut in several parts. Sulfur is a sulfide, and this become carbide. So this is typically a tribochemical reaction due to the nascent surface. We can, of course, confirm this by XPS, but it's maybe not very important, these two. Now I would like to show you another example in another application of lubrication. This is a case of phosphite additives. This is typically this kind of molecules that we use. And the application is a gearbox of your car, if you have a car like that. And we put some additives in the oil here. And these additives are different from the additives from the engine. So they contain this material additives. And this is good additives for gear application. So we'd like to understand how these molecules react with the surface and form the tribofilm which protect the surface. So again, we made in vacuum, we remove the oxide, because in the case of gears, the contact between gears is very severe. And very often the oxide is removed by the gears because the contact pressure is very high, maybe 2 gigapascal. So oxide is removed during the gears and exposed to the lubricant. So we remove the oxide here. We make a friction in vacuum, expose to the gas, 3-methyl phosphate here, and again, we go to the analysis. And this is the result. This is outside the wear scar here. You can see that there is only this peak in the spectrum, XPS. And this is the molecules which is adsorbed on the surface. The molecule is adsorbed at the surface anywhere, in any place. But inside the wear scar, you see the molecule which is adsorbed, but there is a new peak, new chemical species here. And this chemical species is iron phosphide, FeP, phosphide, different from the phosphite. Okay. So this is a new compound formed by the tribochemical reaction. And even inside the wear scar, UHV wear scar, there is some phosphide also. So the additives can react with the tribostress surface without any sliding. This is a very interesting case of the effect of a nascent surface. It's like a catalytic action. And this is a friction coefficient of steel in vacuum, very high friction. And we introduce the gas at different pressure. We increase the pressure, friction decrease here, 5 hectopascal. And this is very close to the liquid if we make the test with the liquid, with the tribometer. So we have a good simulation of liquid phase lubrication by gas phase lubrication with some hectopascal of the gas. This is not so important. Now the mechanisms quite complicated because starting from these molecules, we have to these surface products, phosphide, iron. So this is a chemical pathways we can imagine to come from this molecule to this compound, phosphide, and maybe other species form methoxy. So this is really chemistry. And of course, it is difficult to analyze by XPS. For example, here with the carbon peak, we can find some carbonate peak here. And in the oxygen peak, we can detect peaks. Well, difficult to identify exactly. So here we use computer simulation for this case. Maybe you learned this morning in the news that Nobel Prize of Chemistry is molecular modelization, and this is very important also in tribology. We used a lot of computer simulation, and this was made in Italy by Professor Rigi, and for example, Professor Rigi used a TMPI, so the same molecule as we used also, and pure iron surface here, iron 1110 surface. This is okay. This is a iron surface, and on this iron surface, you can have different site for adsorption. And this is the molecules here. And if the molecules adsorb to the surface, she adsorb here by the phosphorus, and she adsorb on this site. But after she is adsorbed on this side, the molecule cut here. You can see the next. There's only two termination. And now there is another site on the iron surface with the 2 iron atoms. And it continues like that, cut again here. And now this is another site which is concerned on the iron surface. And finally, it's cut here, and you get the phosphide. Iron phosphide that we analyze in our experiment. So by computer simulation, we can see exactly the pathway of reaction. So you can see here the molecules arrive here and finish here, and finish like that. And the other fragments get at the chemisorb also on the surface. So we can modelize, in this case, we were able to modelize by DFT calculation the reaction of the molecule with a pure iron surface. Now I will change another topics with borates, another additives. And we use a borate because in the engine we use phosphates. But the problem is the phosphorus, because the phosphorus has to be removed from the oil. So there is a regulation coming more and more severe to remove phosphorus. So the idea is to replace phosphorus by boron. At the moment, boron is not no limitation, but maybe in the future there will be limitation also, boron. So again, we made some friction tests with the same approach as before, and this is a vacuum, steel on vacuum. We introduce low partial pressure of the 3-methyl borate, increase the pressure, and 5 hectopascal, you have a reduction of friction, yeah, from 1.6 to 1.2. And this is to be compared with the liquid phase of TMB. You can see that it's not very different. And you can see here the tribofilm, which is formed in the wear scar. This blue colored here, this is an optical micrograph of the tribofilm. This tribofilm protects the surface from wear and decrease the friction. This is typically the role of the additive in the lubricant, to decrease the friction and to protect the steel surface from wear. So here we use Auger spectroscopy. We analyze inside here the tribofilm. And you can see here the surface. And here we ion etch the tribofilm to see what is inside the tribofilm. So you can see that boron is here in the tribofilm. So there is reaction of borate with the surface. And here we are now in the steel surface. So only iron is present. But if you look carefully at the oxygen peak here, you have different form of oxygen. You have the tribofilm, which is here, and you have the iron oxide, which is below. So the borate is at the top, and the oxide is below. This is because there is a chemical shift here in the energy of this peak, and we can recognize the oxide from the borate. So we can see exactly, for example, if we have a profile like that, we can see that in this wear track, we have less iron, we have borate, less oxide, and boron. So typically, we were able to see the reaction of the borate with the oxide. Okay, all these reactions that I showed you before, sulfide, phosphide, borates, can be explained very, very easily by the HSab principle. So this is a classification of an acid and base. And according to this principle, soft acid prefer to react with soft bases, and hard acid prefer to react with hard bases. This is well known in chemistry, and you can see here that it works because, for example, metal atoms like iron prefer to react soft, with sulfide, and with phosphide. And hard species like oxide prefer to react, with phosphate. So, and the same with borate. So we can explain this chemical reaction by this kind of principle. Now I would like to change a very different topic, but always with the gases. Friction of titanium alloy in presence of nitrogen. Here, the problem is a engine plane. It's a wear problem. So here you have the blade, and each blade is connected to the rotor, to the disc here, by this friction system. And during the motion of the blade, rotation of the blade, there is a centrifuge force here, and this push this part on this part. And there is, of course, some vibration during the flight. So there is a wear in this area. So, of course, we have to reduce wear in this area. Otherwise, you have to change the blades after a certain number of taking off. This is typically, we call this a fretting damage in this area. So this is working in air, of course, in humid air sometimes. And if we look at what happened, so typically we are with titanium alloys, and there is a coatings. Coatings is this one, complicated. But this is a situation at the beginning, and after a certain number of rotation, you can see that there is some wear here. So this wear, and this wear also in the titanium pieces. So damage. And these damage are very severe. So we want to explain why there is a lot of wear in this area. And from the analysis, it was detected that this pink material is made of some titanium oxynitride carbide layer. And this is very hard material, much harder than titanium alloys, and this where the hard particles here make the wear of the two pieces. So explanation, for example, nitrogen, why the nitrogen can react with titanium. It's very normally titanium is react with oxygen. So we made the experiment, same as lubrication. So here friction in vacuum, put the gas. Gas here was nitrogen. And again, friction and analysis. This is very interesting. This is a friction in high vacuum, titanium alloy high vacuum. You can see that there is a very small wear scar. This is the image of the surface after the friction test. Wear is very small. But if we work in high pressure of nitrogen, here you can see 800 millibar, a lot of wear appear. And in air the same. Sorry, we have no image here. So wear is drastically enhanced by the presence of oxygen and nitrogen. And now if we look at the surface, typically this is an iron-edge surface, this one here, after exposed to the gas. As you can see, it's maybe complicated, but you look at here, there is no nitrogen on the surface. So the gas here does not react with the tribostress surface, contrary to the case I showed you before with sulfide, phosphide, and so on. Here we use a iron-edge surface, and we expose to 800 hectopascal of air. And again, you can see here, there is no nitrogen on the surface, not in the first wear scar, and no nitrogen in the second wear scar. This is only a little bit of oxygen because Professor Sugimura knows this very well. There is a very small oxygen content in the nitrogen, and only a very small oxygen content can react very quickly with the titanium, because titanium reacts very reactive toward oxygen. But now we made the friction test with the nitrogen. Friction with 800 hectopascal of nitrogen at 350 degrees. Typically, this is the temperature of the engines at this part of the engine. Here you can see that the nitride peak is coming here. And not only the nitride, but the carbide peaks. The carbides come from some hydrocarbons present in the nitrogen also. So we were able to reproduce the formation of the nitride, and this nitride layer is very hard and provokes the wear of the alloy that you see here. So we explain this behavior. Now, I would like to talk about another problem, but this problem is maybe more close to your problems. This is a case of DLC coatings and gas phase lubrication of DLC coatings. This is I'm sorry, I'm not able to traduction of Japanese, but this is a Nissan car, just released now. And this is a small engine here, which is used here. And this engine is here. And these engines contain coatings. And typically use TAC coating. TAC coatings in this part of the engine, which is a valve lifter. This is a tribological part, very severe in the engine. And the second part is the friction of the piston rings on the cylinder. And you have here the rings. And the rings can be covered with the coatings. This is mass production at Nissan. And I forgot to say that the lubricant is a special lubricant containing alcohol molecules. So we want to explain why we have good performance with this engine, 27 kilometers per liter of gas, because the friction is very low. We decrease the friction here, we decrease the friction here. What is the mechanisms of the friction reduction in this case? So, again, we use a machine. But here we use the machine more simply. We just made the friction test in presence of the gas. For example, here we have the friction coefficient. And this is a number of passes between. This is a number of cycles. And by TAC. TAC is a hydrogen-free carbon coating. Very, very hard. Not so hard than diamond, but maybe 60, 70 GPa, and diamond is 100. Steel is 10. So 70 GPa is very hard. So if you make the friction test in a high vacuum, you can see that it's not good, because friction at the beginning is low, but this is because the contamination on the surface. Once the contamination is removed, friction increases to 0.8. And of course, this has no interest for application. But here we introduce 60 hectopascal of hydrogen. You can see that at the beginning, there is no change here. And here you have an increase, like in the vacuum, under vacuum. And in this, in the part of the friction test, we of course stressed the carbon surface, and we made some dangling bonds on the carbon surface. And once these dangling bonds are produced here, hydrogen react with the surface. Not immediately, you know, at a certain time, but after 200 cycles, it decrease to 0.02. So you can see that the reduction of friction is very, very high, more 20. So hydrogen can lubricate carbon. That's the first point. But of course, hydrogen was not our interest in this case, but it's your interest. So of course, we can look at, for example, the effect of the pressure of hydrogen on the friction reduction of this coating. Here we made the same experiment, but using water. Water. In this case, it was deuterated water, but anyway, it's the same. So friction in high vacuum, here. High vacuum, very high. We introduced 10-2 hectopascal, very, very small pressure in green. Practically no effect. We introduce 1 hectopascal. 1 hectopascal is red. So you can see what happens. Same story. We produce the dangling bonds, and water react here with the surface and give the low friction, very stable low friction. And if you can increase the quantity of water to have this low friction. So again, there is a reaction of water with the carbon, which produce the low friction. We made also the experiment with ethanol. And again, we have the same story. 10-2 hectopascal is sufficient to get the low friction. So a very low concentration of ethanol is needed to lubricate. This is another gas, glycerol, same story. In this kind of experiment, it is very interesting because you have no rheological effect because the molecule is in the gaseous state. There is no liquid, no hydrodynamic lubrication. So, to summary, you can see that hydrogen react, lubricate, but high concentration are necessary. For methane, even high concentration are needed. But for water, small concentration, and for these two alcohol molecules, very low concentration are sufficient to lubricate the carbon. So what mechanisms in playing now? So starting from this, this is the situation of the coatings after deposition. It contains a lot of sp3, and the surface is terminated by many, many groups, H, OH, O. This is the surface of the DLC when it comes from the supplier. This was coating were made in Japan by ITF company. So we suspect that after this, the reaction with ethanol give this. We suspect this. And this is lubricate, and this does not lubricate. But of course, this is very difficult to analyze. So again, we use the computer simulation. This computer simulation was made by Professor Kubo in Sendai. So this is a modelization of the carbon here and the second carbon. The high pressure between this and this, 1 GPa, sliding and putting a molecules here of methanol. Maybe I can show you This is the experiment, computer experiment. And there is four methanol molecules. But you can see that the methanol molecules is cut in small pieces. And each pieces react with the carbon coatings. Here, methane is formed. And at the end, you will see some OH termination coming on the surface. Here, for example, OH termination. So if you have a lot of molecules, at the end, you get a lot of OH termination. And importantly, the surface become hydrophilic because there is a lot of OH on the surface. So this mechanism has been confirmed by a computer simulation. Okay, so this is the original situation. And after friction, you can see here what happened. You have OH termination. Even you can produce water. So this is very interesting because I have no time here to talk about that. But we can lubricate with alcohol species, and this species transform into water in the contact. This morning I visited the Tribology laboratory where they study hip joint and so on, and they look at the lubrication properties of water. Water is a good lubricant, but unfortunately it is not viscous. But here you can see that the water can be produced inside the contact area. Okay, so I would just like to show you our new machine because I showed you before was made with a previous one. And this is our new installation here, you can see. So now the tribometer is here. And here we have a preparation chamber. And in this preparation chamber, we can heat, make the coating deposition, magnetron sputtering, and so on. And now the new spectrometer is here. So with this machine, we'll have much more possibilities to study gas phase lubrication in the future, and particularly to introduce two gases at the same time. Okay, that is my group at Ecole Centrale. So you can see that there is a female and male at the same. Normally, tribology is more mechanical engineering, so not interest for girls. But here we are because we look at the chemistry issues, so we are they are more interested in our research. Okay, thank you very much. If you have any questions.